All right, so welcome back. What we're going to do this time is I'm going to take the same functions here and we're going to find the antiderivative, the integral. Now remember last time we started with the chain rule and then we found a pattern and it became a part of our DNA. We remembered that when we take the derivative, we multiply by also the derivative of the stuff inside the bracket. So we're going to start out doing it the slow way, and then we're going to generalize it. So for the first case, we want to find the integral of cos of 3x with respect to x. So let's write that out in our working. We take the 3x stuff inside the bracket and we say, okay, let's throw that into a bundle. Let's call that u. So we take u, which depends on x, and u is 3x. Okay. Now, the problem is my integral becomes integral of cos of u. That's fine, but I'm integrating with respect to x still. That dx. Can't get rid of it, it stays there. So I think to myself, I wonder if I can change it. And I say, why, yes, I can. If I take the derivative of u with respect to x, which I can totally do because here we have u and u depends on x. Derivative of u with respect to x is 3, and then I'm going to rearrange it by multiplying everything, both sides here, by dx. And then I'm going to divide by 3. What does this tell me? This tells me anywhere I see dx, I can replace it with du over 3. So this becomes all of that integral of cos of u with respect to u over 3, and now I just take that over 3 and I bring it out the front. So this is like 1/3 times integral of cos of u with respect to u. Integral of cos is sine, so this becomes one-third of sine of u plus a constant, and we know that u is 3x. So here I can write my answer. Okay. So this looks like the normal integral of cos. There it is. And then we divide it by 3. But 3 is the derivative of the inside of the bracket. So we're going to do another example and we're going to test. We're going to test and see if this rule works. All we do is we find the antiderivative and then divide by the derivative of the bracket. Okay, so let's find the integral of sine of negative 7x with respect to x. So we take that negative 7x and we throw it in a bucket called u. We substitute it for u. So u equals negative 7x, and now the integral becomes integral of sine of u with respect to x. We need to get rid of that dx. We need to change it to a du, so we integrate with respect to u. So I can find derivative of u with respect to x, and that's negative 7, and then I just rearrange the same way, so multiply both sides by dx, divide both sides by negative 7, so anywhere I see dx, I can swap it out with du over negative 7. So I see dx here, I substitute it, then I take that, divide by negative 7, bring it out the front, okay, now the integral of sine is negative cos, so we have negative 7 times negative cos of u plus a constant, and you can kind of just leave the constant and not worry about dividing it by negative 7 because, well, a constant divided by negative 7 is still a constant no matter what happens to it. So we can say, I'll just write that straight in the answer. Negative 1 times negative 1 over 7 makes positive 1 over 7. And u was negative 7x, so I swap that back, plus a constant. So, that's looking pretty good. Looks like the pattern. So we can use the pattern. Using U-substitution, I know that derivative of e to 2x is like e to 2x, but then I have to divide by the derivative of the bracket. Derivative of that bracket in there is 2, so I divide by 2, which is the same as multiplying by a half. And I can do the same thing over here. Again, we have a bracket. When you take the integral of something to a power, you increase the power by 1. So the power goes from 4 to 5. Then you divide by that bigger power. So you're dividing by 5, which is the same as multiplying by 1 on 5. And everything inside the bracket stays the same. There we are. And then we have to divide by the derivative of inside the bracket, which is 1, so we're just dividing by 1. Oh, remember, always add a constant. Dividing by 1 doesn't do much in this case. So we add a constant. And there we are. I'm going to modify this one a little bit. I'm going to say it's all this stuff times 3x minus 4. And I'm going to go ahead and do it the long way, just so... let's change that. Let's change it to... I'll be really unimaginative and change it to 6x minus 4. So let's do that the long way. Okay, so we want to find the integral of this thing here. Let's write it down. We're finding the integral of 6x minus 4 times 3x squared minus 4x to the power of 2 with respect to x. So I look here and I say, right, I have two sets of brackets. The second set, its derivative is going to be 6x minus 4. That's why I said I was being lazy. Doesn't matter. And there it is. So I'm going to do a U-substitution, and I'm going to say U equals 3x squared minus 4x. So now my integral becomes 6x minus 4 times u squared with respect to x. I don't like that with respect to x. I also don't like that there's an x here. I want to get rid of it. So let's go ahead and take the derivative here. We can take derivative of u with respect to x, and that makes derivative of 3x squared. We take the 2, multiply it here. 2 times 3 makes 6. Decrease that power by 1, so we have 6x. There we are. I'm going to put brackets around that just to keep it safe and nestled in there. All right, now multiply everything by dx. Then divide everything by the bracket 6x minus 4. So everywhere I see dx, I can swap it out for that thing there. So over here I have my question so far, and I take dx, swap it out here, so dx becomes du on 6x minus 4. 6x minus 4, divide by 6x minus 4. Well, that means those two just cancel out. And my integral becomes integral of u squared with respect to u, which is increase the power by 1 up to 3, divide by 3, add a constant. So if u was 3x squared minus 4x, my answer here is going to be 3x squared minus 4x, to the power of 3, divide by 3, and add a constant. And there we have it. I just wanted to verify that it worked, because sometimes when you see brackets, it gets nerve-wracking, but also sometimes it isn't. So, same pattern. All right. Well, I hope you had fun. Grab your textbook, do lots of exercises, and I'll see you next time.